Hello, Algebra Students. Mr. Lawrence here, and we're going to be talking about a different kind of function today. Yesterday, the weekend video, and then yesterday in class, I guess if you're in level 2, then it wasn't the weekend video, but, the previous video, um, we talked about, like, a man walking down the steps, right? And we were able to make a little graph. Hold on, my cord is getting in my way of my airliner. Okay, and we had a graph, and we were able to compare the elevation, right? How high the person was versus the time. And remember, this is like our x-axis. It is our x-axis, the time, and that is our independent variable. And then the elevation is our y-axis. That's our dependent variable. Now, one thing we found was, maybe in the stair example, the guy was up here, and then after so much time, he went down for a little bit, and then it kind of went horizontal, and then went down a little bit again. Okay, and he's walking approximately the same rate, and then, once he eventually got down to ground level. Now, this graph is made up of line segments, right? Because his rate of motion was constant. And we were able to use this equation, d equals rt, to determine how fast he was going down. We plugged the distance in, we plugged the time it took him to go that distance, and we divided to get r alone, and that gave us our rate. So we knew his constant rate of travel. This would work for a person riding on a bicycle, okay? Perhaps, we have somebody riding on a bicycle, and again, we're going to put the time as our independent variable, okay? And then it wouldn't be elevation, it would be distance, and we're talking about distance they've traveled, not necessarily distance from their starting point, because if they're leaving from home, then it might be pretty safe to say they're going to return home, and so I'm not actually talking about that situation. And so after so many minutes of riding, we know the person is here, and if there's a plateau for a short time, we can maybe try to figure out what happened, and then we found that they rode another distance in this amount of time, okay, and then it stops. And remember, this part is steeper here, right? This is a steeper part of the graph, so he's riding faster, riding at a greater rate, a faster rate, okay? And here, he's not moving for a period of time, not moving. Well, why isn't he moving? Well, or she, maybe they stopped to rest. Maybe they got a drink of water. Maybe their chain jumped and they had to get off and fix their chain, something like that, okay? And then here we notice that they're riding a little bit slower. It's a slower, less steep incline, so it's a slower rate. And it could be a lot of things. Maybe they're going uphill. Maybe they're tired. Maybe the stop had something to do with an injury. Maybe their calf cramped up, and then to finish their ride, they had to go this distance from here to here, but it took a longer period of time. Notice how this, the distance here, it takes a lot more time than the distance here. And I'm always talking about how high they went, or how long or how far they went, because the distance is going vertical. Now, this is not always the case in a graph. Those produce linear equations, by the way. Remember we were graphing y equals 1/2 x, okay, or we had the equation y equals 4x minus 5, or maybe even 3x minus 2 equals 5x plus 7. These are all linear equations. And what do you think the root of linear is? Well, it's not here, it's line, okay? These are linear equations. They will produce a line. And I know that because the exponents on the variables, I'm sorry, I need a y in there. Sorry about that. The exponents on the variables are all 1. Some of you are going to say they don't have an exponent. Sure they do. They all have a 1. When we don't see an exponent, we assume it to be a 1. Okay? So those are all linear equations. But not everything moves in a linear path. For example, let's say that you've got a person here standing on a cliff, okay, or at the edge of a ravine, and they're throwing a rock off. Okay, here's my rock. Now, the rock, if they throw it, it's going to go up here, right? And then, eventually, at some point, it's going to fall. Now, think about it. The ball is moving upward, or the rock is moving upward, right? But there's something trying to keep it from moving upward. What is that something? Well, of course, it's gravity. Gravity is pulling down on the ball, right? Gravity is pulling down this way, pulling it back towards the earth. So if the ball leaves the hand at a certain speed, and the ball reaches a max height of here, you know, how high the person threw it, or the rock, I keep calling it a ball, what is happening to the ball as it gets to this point and then starts to fall again? Think about that for a minute. You throw the ball up in the air. Maybe test this. Take a ball of paper. Okay, don't throw rocks at windows, but take a ball of paper and throw it up. Throw it as high as you can, and of course it'll go up and then come back down. So let's think about what must happen. Well, if gravity is pulling it this way and it's trying to go up, gravity is going to win the fight because you can't throw it hard enough. It has to be slowing down. I can't pause the video. Sorry about that. My wife wanted to say something, but she's just going to have to be patient. I'll go ask her what she wants after the video. Anyway, so the ball starts slowing the instant it leaves my hand. Why? Because gravity is pulling on it in the other direction. What's the rate? How fast is the ball moving at the vertex, at the highest point? It actually has a rate equal to 0 feet per second or miles per hour or whatever units we're using. And then as it starts to go down, it speeds up again. So here the ball is speeding up, or the rock is speeding up. So if the rock is speeding up, isn't it safe to assume that it's going to cover a greater distance vertically in the same amount of time the further away from the vertex it is? Let's think about this. Let's say it takes 1 second to go from here to here. Okay, 1 second. Now, of course, it's traveling along this black path here, but let's say it takes 1 second to do that. Well, in another second, and let me do this to kind of, okay, in another second, kind of clone you, thank you. So that's another second, and let me drop this down, okay. So you see this triangle, right triangle I've made. Now look at this one. To go back to the black line, the back curve of the ball, look at how much longer this blue segment is than that one. Hasn't the ball fallen much, much farther? I mean, look at that, compare them. Here, let me put it on a graph for you. Let's see if we can make it even look a little more exact. So, okay, here's a little homemade graph. Actually, you know what, let me just get some graph paper out. That would be even better. Okay. My content, pictures, shoop, there we go. Okay, let's see if I can fit this onto my graph. Okay. Hey, that fits pretty good, right? Okay, and let me get that curve shape. By the way, that's called a parabola or a parabolic trajectory. It is impossible to throw a ball in a straight line horizontally because gravity is constantly pulling it down. Now this won't be a perfect parabola, but I think it went something like this, right? Okay, and let's see here. Our vertex appears to be right about here, okay? And that looks like it's at half a second, 1.5 seconds. So the distance from here to here looks like it's 2.5 seconds, or 2.5 squares, if you will, right? 2.5 squares. So now let me go from here. Let me go 2.5 squares the other way. So let's go 1, 2.5 right there. Okay, that would be 2.5 again, right? Now let's do this. We'll get a segment here. I'm going to go from the vertex. This is the vertical distance the ball has fallen. Let me change the color of that so it stands out a little bit more. Oh yeah, that's good. Okay, and then let me do one here, going from the 2.5 second mark down, and that's not quite over, so I'm going to move it over a little bit. There we go. Yeah, that's pretty close to parabolic. And check it out, isn't that second one greater than the first? Here, I'll make it purple. Didn't the ball go a greater distance downward in the same amount of time? See, here's the distance downward, the green one. And look at how much bigger that is. Yeah, now I'm not using actual data for this, but I'm just trying to get the concept. Now, let's go another 2.5 seconds and see what happens. Okay, so half is here, so 1.5, 2.5 would be here, right? Let me get the vertical segment. Where is it at? Segment, where did you go? Okay, here it is. And this one going straight down. Okay, it looks a little bit closer to the purple one in size, but if you compare them, look, it is a little bit longer. So in other words, the longer the ball or the rock falls, the more distance it covers. Well, if you're covering a greater distance, like let's say you and I are running a race, okay, and we run for the same amount of time, but you go a farther distance, what can you assume? That you must be going at a greater rate. So what the ball must be doing, or the rock must be doing, it must be speeding up. Because here we have the first distance in 2.5 blocks, and then here's the second one, and then here's the third one, and you see that the ball is, or the rock is speeding up. Now, this isn't done very well. It's not a great graph, etc., but it does demonstrate the point that it's going a larger amount the longer it falls. And it doesn't matter what time interval you use, it is going to go farther. What this is called a quadratic. Okay, this is a quadratic equation. A quadratic. And quadratics can be used for a lot of things, one of which is describing how things fall. See, things don't fall the same rate the whole time. Now, when we talk about falling things, most of the time at the Algebra 1 level, we're going to talk about falling in a vacuum, meaning there's no air resistance, okay? In the real world, there is air resistance, and when you get up into higher level classes, maybe a physics class, you'll calculate how long it takes something to fall with air resistance. But the same object can have different amount of air resistance based on how it's oriented. Take a piece of paper that's not folded or crumpled or anything and just drop it. It takes a long time to fall. Take the same piece of paper, crumble it up into a ball and drop it, and it'll fall pretty directly to the ground. It won't take all that long. The second case has very little air resistance. You reduce the air resistance, and so therefore the ball falls faster. Race cars have kind of a streamline design, where they kind of slope and go back like this. Okay, that's air resistance. That's to reduce air resistance. The air passes over the car and allows it to go faster. If the race car was built like this, okay, now it's driving this way, the air would hit this wall in front and have nowhere to go, and therefore slow the car down a little bit. Okay, frisbees have a low level of air resistance when they're thrown horizontally because they're nice and thin. Now a kite has a lot of air resistance, and that's why it's able to fly. Okay, at least in a simple understanding. If you just take your basic kite, the air pushes up on these parts, causing it to go up into the air, and then you got your string down here, and maybe there's some lightning in the background. You're trying to play Ben Franklin. By the way, don't do that. Anyway, all right, so quadratics. Now, quadratic equation, we're not going to be doing much with them, but we're going to realize that they explain how certain things move, and their graphs will look different. Their graphs will always be parabolic in nature. They will be parabolas, okay? And their equations are going to look like this. Yeah, things like that. They don't have to be 4 and 4 there. But you notice how all the exponents aren't 1. Now all of a sudden we have an exponent of 2. This exponent is 1, that exponent is 1. But this exponent here is 2. And that will produce a quadratic equation. All right, so tomorrow's class, we're going to be watching another video, making some more graphs, and trying to answer some questions. That's it for tonight. Mr. Lawrence signing off. Have a good night, everybody.